All right, so chapter 12 builds on a lot of things that we've kind of talked about generally. We've talked about what solids, liquids, and gases are. We're going to talk more in this chapter about what makes them solids, liquids, or gases, why those things are even different. And we're going to talk a lot about intermolecular forces. So there's going to be a lot of general stuff that we have already sort of covered. So we're going to get some slides about solids, liquids, gases. I'm going to gloss over most of it because I think you're familiar with most of it. And I'll highlight those things that you need to be taking away from those slides. I thought these were, well, we'll see if these are the ones. I made some edits. Yeah. I did make some edits to these slides. They're not huge. I just tried to condense a few things. But they should be still very similar to what you have downloaded, if you downloaded and printed them. Okay. Interactions between molecules. Basically, nothing happens if there are no interactions between molecules, right? If every molecule or every atom bumped into each other and literally nothing happened, then nothing else would happen, right? So we are living organisms because of the interactions of all of these atoms and molecules in these self-perpetuating chemical reactions, which is a wild way to think of it. But even the flavor of most foods comes from these interactions, and specifically the interactions of the molecules with your tongue. So that's actually a caffeine molecule there. Need lots of that personally. But moving on, the specific interaction between molecules in coffee that tastes bitter, which one of those main bitterants is caffeine. And the taste receptors on the tongue is caused by the intermolecular forces. These are attractive forces between molecules. Intermolecular forces, I would argue, are essential for every physiological process. There are less specific intermolecular forces that exist between all atoms, molecules, and atoms. And intermolecular forces are responsible for the very existence of liquids and solids. So the physical state of matter depends on the strength of the intermolecular forces relative to the amount of thermal energy. So if you think about this as the atoms and molecules have different levels of being sticky. And the more sticky they are, the harder it is for them to get away from each other. So when they run into another atom or molecule, if they're really sticky, then they stick, right? And if they're sticky enough, they won't move around each other either. So this attraction between the molecules is this sort of sticky factor. And if you add heat, you add energy, you're essentially pulling apart those atoms and molecules more strongly, right? You're using more force to pull them apart. So the intermolecular forces are how sticky they are. The thermal energy is the energy trying to pull them apart. So more scientifically speaking, the energy associated with motion is called thermal energy. So by increasing the thermal energy, increasing the temperature of something, you're giving them more motion, more energy. So if you have substances that have weak intermolecular forces or only a little bit sticky, they are, at any given temperature or thermal energy, more likely to be gases. If the intermolecular forces are strong, so if they're really sticky, then at any temperature or thermal energy, the sample is more likely to be liquid or solid. This is kind of the prevailing concept throughout this chapter, is what determines if a molecule is sticky, and how does that affect the way that it behaves. So some properties of solids, liquids and solids. Gas molecules, as we talked about in chapter 11, are separated by large distances. That's part of kinetic molecular theory. Also part of kinetic molecular theory was that they don't have any attraction to each other. So they're not sticky at all. So these gas particles are super far apart, and when they do bump into each other, they don't stick at all. For solids and liquids, it's all very, very different. So they are touchingly close, which we've talked about. And so they're essentially in direct contact with each other all the time. The difference between a solid and a liquid is the freedom of movement of the molecules or atoms. So in a liquid, they can shuffle around each other, but in a solid, they're pretty much locked to their row, to their location. So some images of what these would look like, right? The gases have huge spaces in between them, whereas the liquids are touching, but they're still sort of disorganized. They're able to move around each other. The solid is perfectly aligned. And actually, I did find another simulation of this. So we hit play here. Let's go to solid. So we've got our block. You can see that they are jittering a little bit. They're moving, but only in their spot. They don't go outside of that. And if we increase the temperature a little bit, that starts to fall apart. They start to move around. You'll see that even some of them do float away and become like a gas. Although if they come back and they touch the pile again, they'll probably stick. All right, so that's more like a liquid. And then if we add more heat to this, we give them more kinetic energy, they start floating away and separating from each other. And then these ones don't like to condense. So as I cool it down again, now you'll see as they hit each other, they stick. Everything starts to fall to the bottom. And eventually they form a sort of solid, although not as pretty of a solid as we had before. Right. But again, they're locked into place for the most part. Mm-hmm. Yeah, so this would be your ice. Heating it up would be water, and then, yeah, steam. So we will come back to that. Okay, so properties of gases. This is where I said I'm going to sort of gloss over most of this because these are things that we've covered before. If you want to go back and review them, you can either review them here in this chapter or go back to chapter 3 or 4, I think it was. The key here is that they have weak intermolecular forces relative to thermal energy. So they're not very sticky. Right? Things that are generally gases, and we're kind of talking here gases at room temperature, they're not going to be very sticky. So whenever they do run into each other, they're just going to bounce off. As we increase that stickiness factor, when they do come into contact with each other, they're more likely to stick together and then find another particle and stick to that particle, and then eventually dropping out and condensing. So liquids, and like we saw in the simulation, they have high density in comparison to gases, but they have moderate intermolecular forces relative to thermal energy. Right? So they're stickier than gases, but not as sticky as solids. So they can't get away from the rest of the molecules, but they can move around. They're not locked into a single position. So example being liquid water. Solids also have high densities. Again, that's because they're all packed and touchingly close. There's not a lot of space in between them. They have strong intermolecular forces relative to thermal energy. So they are stuck together, and not only are they stuck together, but they're also stuck in whatever position they're at. So they cannot move around the other molecules. And in something like ice, they form these crystal patterns. And we'll talk about, I think we'll talk about why they do that also. So sugar, another example of a solid. So this stickiness leads to some properties about solids, liquids, and gases, in addition to the ones we've already talked about. One of them for liquids is, or actually two for liquids, I should say, are surface tension and viscosity. So without any intermolecular forces, we'd have solids and liquids wouldn't exist. Right? If the particles didn't stick to each other, they would never condense into a solid or a liquid. They would just continue to bounce off of each other, and everything would be a gas. there would be no, there'd be nothing as we know it, just gases. So surface tension and viscosity, as I mentioned, come about as a result of intermolecular forces because the water molecules, or really the molecules of any liquid, stick to each other. So you can take a paper clip and actually float it on the surface of water because the water molecules are all so stuck to each other that the paper clip can't get in between any of those water molecules. And of course, this depends on how you put the paper clip into the water. If you go like edge first, it will punch through those water molecules. But if you lay it down flat, it'll sit on top.
Is that why it comes from like belly flopping?
Yeah. So as a quick as, if you belly flop into the pool, what's happening is the faster that you hit the water doesn't want to let you in, and it all compresses, and then it relaxes after a little bit. So yeah, that's why it hurts when you belly flop.
Yeah, and like you don't have the angle to break the surface tension.
No, that's exactly it. Yeah. You're not breaking that surface tension. You're just, landing on your face. Not very good at breaking surface tension. So, so if you place it on the surface carefully, again, they're all stuck together. They don't want to let anything in. They will if they have to, if enough force is applied. So I went and copied and pasted this image of a paper clip. So these, water molecules are all interacting with their neighbors. And one of the other things that comes about because of the surface tension, one of the other things that adds to this, like resisting things entering the water, is that the water is also trying to pull in towards the center of the water, which is a little bit weird to think about. But these water molecules on the surface are interacting with fewer than the molecules on the inside. So these ones are more tightly stuck to each other. These ones want to be in on that group hug. So they want to get into the middle. So that's what causes the surface tension, it's that stickiness. If you tried to belly flop on something like gasoline, which is not recommended, it would not hurt as much because there's not as much surface tension. It's a much less, it's less sticky. We'll just keep using that analogy. The intermolecular forces are weaker. So water drops are also spherical because of this. The water molecules are all trying to pull as closely to each other as possible. And if you get a big water bubble in space without gravity, this one's not quite perfectly spherical, but it is mostly spherical. It's the projector.
Oh, I was like, are they holding their breath?
No, the projector is terrible. They are kind of red, but. So another property that comes about as a result of the stickiness is viscosity. So liquids can be thicker or they can be thinner, right? And you think about pouring syrup or pouring honey versus pouring water. And we don't really work with organic solvents in this class, so we haven't really, no, you've probably seen isopropyl alcohol is a thinner liquid, like it behaves differently than water does. And that's because it's less sticky. It has fewer or weaker intermolecular forces. So because it's not sticking to itself as much, it pours easier. So this stickiness of the individual molecules means that they can't move around each other as easily. So they can still move around each other, but the more viscous, the stronger the intermolecular forces, and flow is hindered. So like motor oil compared to gasoline, or honey compared to water. All right. So evaporation or vaporization, you're probably familiar with, boiling water, right? You're vaporizing or evaporating water. It's a physical change in which a substance is converted from its liquid state into its gas state. So we're adding enough thermal energy to break these, or to overcome the stickiness between the molecules. Right? They're moving around fast enough They're energetic enough that they can overcome that stickiness. There's a few things that will affect the rate of vaporization. So if you have a larger surface area or an increased temperature or decrease the strength of intermolecular forces. Right? So something like isopropyl alcohol evaporates really, really fast because it has weak intermolecular forces, as compared to water, which evaporates much more slowly.
Is it true that when you're boiling water and you put salt in the water, it makes it boil faster?
It does. It does. And we're going to talk about that. It's at the end of this chapter, but we'll actually go over the math. Or actually, no, it's in the next chapter. We talk about that. It's called boiling point depression. Or, no, it's boiling point elevation. It makes it boil at a higher temperature. Yeah. No, takes longer to boil. Yeah, we'll talk about it. But
Is viscosity a sliding scale that results in a solid? Like if a liquid gets more and more viscous, like is a solid just an incredibly viscous liquid?
you can kind of think of it like that. I think one example is glass, but glass kind of is, I don't know if glass is technically like a super viscous liquid. I'm trying to remember. I've got conflicting memories about what glass is because they would pour stained glass so that it was thicker at the bottom. And at some point, somebody thought that that was because the glass was slowly flowing towards the bottom and it became thicker at the bottom. But I think that they found later that it was actually poured that way intentionally because that made it stronger. But I would have to look that up. But yeah, in essence, if the intermolecular forces get strong enough, you would go from a liquid that pours very slowly, like molasses, to a solid, if you could somehow artificially increase that viscosity. Yeah.
Well, what about like, okay, last weekend my kids ate pancakes and they left their syrup on the counter and then I went to go like clean it up and it was like, I couldn't get it off.
Oh, yeah. So that's the water evaporating out of the syrup, leaving only the sugar behind. So you're essentially going from some mixture of water and sugar to just sugar.
It was like not hard.
Yeah.
How was I
But it takes a long time because it has to soak the water back into it. All right, anyways. Good questions, great discussion. Vaporization or evaporation is what happened with the syrup. So we can tie it back in. So liquids that evaporate easily are termed volatile. So a volatile liquid is one that evaporates quickly. If it doesn't vaporize easily, then it's non-volatile. So evaporation is a process. So molecules on the surface, as we looked at earlier, they're less tightly held to the rest of the molecules. So it generally takes those molecules on the surface less energy to jump from the liquid to the gas state. And some of them will break away. I mean, this is the reason that if you leave out water in a glass or in a dish, or if you spill water even, eventually it disappears. And that's because even though it's not at the boiling point, or at a boiling temperature, those water molecules on the surface slowly leave and aren't replaced by other water molecules. So that's the process of evaporation. For any given temperature, a sample of molecules or atoms actually has a distribution of kinetic energies. And you kind of see this in the model over here. Let me make these. Oh, let me play. Let me make these a gas again. And once you get up to a gas, it's just especially evident as a gas that some of the molecules or atoms are moving faster than others. And so the temperature of this substance is not based on all of the atoms or molecules moving at the same speed, but it's an average, a type of average of the average speed. It's essentially the average speed of all the particles. Nope, that's not what I wanted. Okay. So there's this Distribution. So this is like the fraction of molecules. So the higher the line is at any given point, the more molecules have that particular speed. So at a low temperature, right, as things are colder, they'll evaporate more slowly, and that's why in the winter everything tends to stay wet for a long time. Right? There's not as much energy, there's not as many particles that have the energy to evaporate, so they don't evaporate. If you increase the temperature, you're kind of shifting this distribution of energies over. There's still some that are going to have very low energy, but there will be more particles that have enough energy to evaporate. This is also the same reason that we're running out of helium, because there's some fraction of helium that actually is moving fast enough to escape Earth's gravity. And so it all eventually just leaves into space. Yes, because of all the helium. That's why you float in space. So condensation is the opposite of evaporation. So it's a physical change in which a substance is converted from its gaseous state to its liquid state. So evaporation and condensation are opposites. When the rates of condensation and evaporation become equal, then you have a dynamic equilibrium. And that's a really fancy sounding word for the same number of gas molecules are leaving the water as are hitting the water again and sticking to it. So there's always some that are evaporating, but especially if you have there was a water bottle in here at some point that somebody left behind. But if you have a sealed container, or I guess you imagine the inside of my mug, right? There's some liquid in here, but there's also some water vapor. And that amount will be fixed because it's only going to evaporate at a certain rate, but it has nowhere else to go. And so eventually it's going to hit the surface of my coffee again, and it will condense and cease to be a gas and then join the liquid. And so the same number for any period of time, right, over 10 seconds, the same number of water molecules are leaving as are coming back. So that's called a dynamic equilibrium. So it's constantly evaporating, constantly condensing, but both are happening at the same speed. And when you reach a dynamic equilibrium like this, the vapor pressure of that liquid, which is its partial pressure, remember the partial pressure of every gas, or of any ideal gas, is due to the amount of particles of gas that are in the air. So at a dynamic equilibrium, the vapor pressure of a liquid is its partial pressure, in dynamic equilibrium. So there's a dynamic equilibrium in here, and if we could measure the partial pressure of water, then that would be the vapor pressure of water at whatever temperature my coffee's at now. So here's an example. So this is if we just put this water in here, and then it's starting to evaporate, and then eventually particles are evaporating, but also particles are coming back. Water molecules are coming back, and they're sticking back to the water and condensing. And then at some point, there's an equal amount of evaporation and condensation, and then whatever pressure that water is the vapor pressure. So things with higher vapor pressures are usually more volatile. Things with lower vapor pressures are less volatile because less of that thing is evaporating. So vapor pressure is dependent on a few things. It's dependent on temperature. So if you increase the temperature, you'll increase the vapor pressure because you have more energy to overcome stickiness. The other thing you can do is decrease the strength of the intermolecular forces. So if they're less sticky, they will leave the liquid phase more readily or more easily. Interesting thing, though, is that the vapor pressure, and this is a little bit counterintuitive, the vapor pressure is independent of the surface area. So if I take my coffee mug versus, I don't know, like a giant jar or something, the vapor pressure of the water in both of those containers will be the same because same area that's being used to evaporate. This is all assuming we're in a closed system. The same surface area that the water can evaporate from is surface area where the water can condense at. So if you increase the surface area, you increase the rate of vaporization, but you also increase the rate of condensation. And so since both of those increase or decrease the same, then it doesn't matter how big the container is, or small. Okay, so boiling point, actually so increasing temperature increases the vapor pressure. And when we hit a vapor pressure that is equal to the pressure above the liquid, that is the boiling point. So now we've hit a point where the pressure of the liquid vapor is the same as the surrounding pressure, and now all of the liquid wants to turn into a gas and has enough energy to do so. So then we start forming these bubbles spontaneously. Rather than just a few molecules at a time leaving the surface, we get entire pockets of water going from liquid to gas. So in the middle of the liquid, you have enough thermal energy to overcome the stickiness of the water, and it boils. For pots, pans, if you're heating it on a stovetop, this is predictable. It heats at the bottom, so that's where the bubbles form. If you heat it in a microwave, sometimes you can superheat the water before it boils, and then it all boils at the same time. Well, large pocket will boil at once, and then it'll spray water everywhere. Because the microwave is heating the whole thing at the same time, rather than just the bottom. Okay, so the boiling point, actually let me highlight this. Boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure above it. So once you reach the boiling point of a liquid, adding more heat only increases how rapidly the water boils. It doesn't change the temperature. So water boiling, and this was a concept that we used really early on with the specific heat capacity lab. So we took boiling water, and you put the metal in the glass tube in the boiling water, and then used the temperature of the boiling water to determine the temperature of the metal before you added it to your cold water. And the reason you can do that, in part, is because it doesn't matter how much heat you add to water, once it starts boiling, the temperature doesn't change, and will remain at wherever it's at.
So my noodles aren't going to cook faster if I turn the heat up?
No, but they will cook faster if you add salt. We will talk about that. So a mixture of boiling water and steam will always have a temperature of 100 degrees C if it's pure water and if the pressure is 1 atmosphere. So that changes a little bit depending on where you are. But pure water and 1 atmosphere of pressure, always 100 degrees C. And it's only after all of the water has been converted into steam that the temperature of the steam can rise beyond 100 degrees C, which is why steam is way more dangerous than just boiling water. So you're still putting energy into the boiling water, but it's not increasing the temperature, so where does that energy go? The energy actually goes into the process of overcoming the stickiness. We talked about that. And it's at 100 degrees C, all of the energy is now going into taking the water and breaking water molecules apart from each other. And that takes energy. So if you look at a heating curve for water, you start at about room temperature, 20 degrees C. It's heating up, it heats up, it heats up, and then you hit the boiling point, and the temperature curve goes flat. The energy is not just disappearing, but it's all going into taking these water molecules that are in the liquid phase and breaking them apart from the other water molecules. And then once all of the water is gone, only once all of the water is gone, can the temperature increase again. I don't think that simulation does that. Limits of a simulation. So because of this, and we haven't talked about endothermic or exothermic for a little bit, but because of this, evaporation is endothermic. So whenever water is evaporating, energy is required to just go from the liquid phase to the gas phase. And this is why, actually, if you have acetone or isopropyl alcohol and you get it on your hand, that's why it feels so cold. It's because it evaporates so quickly, it's drawing heat out of your hand to do that. And this is also how our bodies cool. And it works well, and that's why like a dry heat is not as bad as like humid heat. Because if it's a dry heat, your body sweats, and then that sweat can immediately evaporate. If it's too humid, now there's already water in the air, and your body sweats, but there's nowhere for that water to evaporate to, and so you just stay sweaty and hot.
Well, that's why you feel sticky.
That is also why you feel sticky, because you're just kind of wet. So, yeah, our bodies use this to cool down, and at some point, at some high humidity and temperature combination, your body cannot cool itself as much as it needs to. And that's where temperature and humidity can be really dangerous, because you will just eventually die because you'll overheat if you don't have any other way to cool yourself off. Let me highlight this too. So the system, which is the water evaporating, is absorbing energy because there's energy required to overcome the stickiness of the molecules. So it's endothermic. So if evaporating is endothermic, the opposite of evaporation is condensation. Condensation is not going to be, but is exothermic. So as water condenses, it actually releases heat to become a liquid. Because there's, it takes energy to overcome the stickiness. Energy is released when those molecules stick back together. And this doubles down on why steam is dangerous, because steam is water vapor. It can, one, be hotter than 100 degrees C, and as it condenses, it releases even more heat, causing even more severe burns. Condensation is also the reason that overnight temperatures don't get as low if the humidity is high, because as the temperature drops, the water in the air will start to condense on everything. This is why grass gets dewy, right? Things, when it is humid, as it cools, will just get wet. It's water condensing out of the air, and as that water is condensing on everything, it's also releasing heat, which keeps the temperature from dropping outside. And then it does the same thing in the morning when all that water starts to evaporate again. It cools everything around it. So generally, temperatures will be more consistent if it's humid. Okay. There's, of course, some math involved, but it's not too hard. So you have this heat of vaporization. And the heat of vaporization is the amount of energy it takes to convert 1 mole of liquid into 1 mole of gas. So liquid water vaporizing to become gaseous water takes 40.7 kilojoules per mole. And this delta H is positive because vaporization is endothermic, so energy must be added to water to vaporize it. I think the last time we talked about delta H was in reference to exothermic or endothermic chemical reactions and how you can use that as a conversion factor to figure out how much energy a given reaction produces or absorbs. So here we're talking about it in reference to vaporization. And this temperature, or this amount, this value changes a little bit depending on the temperature at which the water is vaporizing. So at 100 degrees C, it's 40.7. You don't need to memorize that number. I will give you those numbers on exams. So the same amount of heat is involved when 1 mole of gas condenses, but now it's in the opposite direction. So at 100 degrees C, the gaseous water condensing into liquid water will release 40.7 kilojoules per mole. And now delta H is negative because condensation is exothermic. So you can use the heat of vaporization to calculate the amount of heat energy required to vaporize a given amount of liquid, and use it to calculate the amount of heat required. Wait. Those two sentences are almost the same. But you can use the heat of vaporization as a conversion factor. So there's just some values on here. We got water at its normal boiling point. Other things will take more or less energy. These are all isopropyl alcohol, acetone, and diethyl ether all have weaker intermolecular forces, so they're less sticky. So it takes less energy to either vaporize or conversely to condense. So this is again where unit conversions are going to come in handy. Or unit analysis, I should say. So calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. So only two values here. Start with 2.58 kilograms of H2O. And we know that the heat of vaporization is 40.7 kilojoules per mole. So what do we have to do to our kilograms of water? Turn it into grams first. Yeah. Turn it into grams, because then if we have grams, we can find the moles. So how many grams are in a kilogram? 1,000. So because we have 1 kilogram here, or we have kilograms there, we're going to put 1 kilogram on the bottom, and then 1,000 grams on top. And then we want to convert from grams of water to moles of water. So it would be, all right, hydrogen and oxygen, 2 hydrogens and 1 oxygen, 1.01 and 16.0. So it's 18.02. And that's 18.02 grams of water is 1 mole. And then now, because we have moles of water after that calculation, we can use our heat of vaporization, which is 40.7 kilojoules per 1 mole. Calculate an answer. So 3 sig figs. So we got 5.83 times 10 to the 3 kilojoules of energy. That's a lot of energy. So very similar type of calculation to stoichiometry. You could use this stoichiometry if you like the whole table with the boxes thing. You can do that for this. I did it this way just to sort of separate it, that it's not stoichiometry, but it is kind of stoichiometry. Calculation kind of works out the same. So you can make this a little bit more complicated. Actually, this kind of makes it a lot more complicated. So we have a drop of water weighing 0.48 grams, condenses on the surface of a 55-gram block of aluminum that is initially 25 degrees C. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? So there's two things that we need here. One is the heat of vaporization. Yeah, okay, I got the sign right on that previous one. Heat of vaporization for water. So we're at 25 degrees C, so there's actually a slightly different value that we have to use. So we're going to use 44.0 kilojoules per mole. Just going to write it over here. Okay, so we can figure out, I guess I should say, the other thing that we need to use here is the specific heat capacity. Q equals MC delta T, MCAT. So Q is an amount of heat. And so we're saying here, if we take this water, drop of water, condenses on the surface of this metal, because it's condensing, it's going to release some amount of heat based on our heat of vaporization. And then we're saying that all of that heat goes into the metal block. So that heat becomes this Q. And then we know the mass of the block. We know the specific heat capacity of aluminum. And we have delta T. We have T initial, so we can find T final. So this will start out very similar to the last problem. We still need to calculate how much heat actually comes out of this drop of water. So 0.48 grams of H2O, and we need this to be in moles. So use the same molar mass as we did before. Right, and then we plug in here our heat of condensation, which is actually a negative 44.0 kilojoules.
So if it says condensation in the problem, then we know that our kilojoules is going to be negative.
Yes.
Sorry.
No,
Okay.
that's a good question.
Okay.
Yeah, condensation means that the heat of condensation is negative because it's heat being released from the system.
Will one mole be at the bottom and the kilojoules at the top?
Yes. Thank you. And then, well, let's do this first. 0.48 times negative 44 divided by 18.02. So we're releasing, what's a negative 1.17 kilojoules. Okay, and then for our equation, Q equals MC delta T. M is going to be 55 grams. C is 0.903, and that's in joules per gram degree C, times, and I'm going to expand this out. This is T final minus T initial. And our T initial is 25 degrees C. Can you see anything that we might have to do, or can we just plug in our energy?
Convert kilojoules to joules.
Yeah. So just like with the ideal gas law, where all of the units have to match with R, right, the ideal gas law constant, the number of kilojoules here, or well, kilojoules has to match with the specific heat capacity, which is in joules.
Why was the conversion 44.0 instead of the 40.7?
Because we're at 25 degrees C instead of 100 degrees C.
Oh, I see.
Yeah. Previous problem, we were at 100 degrees C. Here we're at 25, so it's slightly different. Yeah.
Is that on the chart or?
It is on the chart, yeah.
Is this chart gonna be on our exam?
I will just give you the right one to use.
Okay.
Chapter 12 is in the same subject, you know?
Yes. So chapter 12, chapter 13, not chapter 14.
So it's gonna be 9 through 13.
Yes. Nope, not gonna sneeze? Okay. Sorry. Okay, so yeah, we have to convert the kilojoules into joules. And so negative 1.17 kilojoules, just like with grams to kilograms or, grams to kilograms, there is 1,000 joules in 1 kilojoule. So this is going to be 1,170. That's joules. Like I said, this is a tricky problem.
So it's definitely gonna be on the exam, guys. Obviously, yeah.
I like stoichiometry problems better. So I think stoichiometry problems are more important. But okay, so now think about this. So why is this 1,170 joules negative?
Because of the condensation.
Because it's condensation, and it's because it's heat coming out of the water. But now when we're talking about the metal, which direction is the heat going? It's going into the metal.
So our answer is gonna be positive?
So the energy that we add here is going to be positive.
Okay, so we just take that out.
So just keep in mind that you have to keep in mind which way the energy is going. Because if this was a negative, if I put in a negative 1,170, that's saying that the metal block is losing heat, but we're adding heat to it. So we're increasing the temperature. Now we can take this and we can solve it. So 1,170, or actually I'm going to use the whole number I got in my calculator here, which is what you should do also. And then divide that by 55, and then divide it by 0.903. And that'll get us to negative 23.598. And those units are going to be degrees C equals T final minus, wait, why did I put, oh, I see. No, it's not a negative. I used the number in my calculator, which I didn't change the sign on. It's positive there. Okay, so it's positive, so now we take that 23.598 plus 25. Oh. Okay. And we're going to get 48 point, we actually only have 2 sig figs, so 48 will be 49 degrees Celsius is T final. This is another one of those things. We'll say, prove it to yourself that that 1,170 has to be positive, right? Do this math with the negative 1,170, see what happens, and see if that makes sense. Because what should happen is that instead of getting a higher temperature here, you'll get a lower temperature than your initial. And we know that the water drop is heating up, right? It goes toward heating the metal, so the temperature of the metal has to be higher than its initial temperature. That is admittedly a very tricky problem because it takes concepts from before and combines them with concepts that we have now. So this is a great example of like an A-level problem. Right? There would be at most, I would say at most 2 of these on an exam. Problems like this. Anytime you can take multiple concepts and combine them together, that makes a much harder problem. Okay. Melting, freezing, and sublimation. So we talked about evaporation, vaporization, and condensation. The same sort of principles apply to melting and freezing and sublimation. So if you increase the temperature of a solid, right, you get more and more thermal energy, it starts to break apart and become a liquid, and that's melting. All right, so at that melting point, the atoms and molecules have enough thermal energy to overcome the intermolecular forces that hold them at their stationary points and turns the solid into a liquid. So intermolecular forces is essentially the stickiness, as I've been saying it. So when you melt ice, you're breaking free, those molecules are breaking free, becoming a liquid. And just like with boiling, if you have water and steam, the temperature can't go above 100 degrees C. If you have ice and water, the temperature cannot go below 0 degrees C. And again, we're talking pure ice, pure water, right? Nothing else in there. Which is why a drink will stay cold for so much longer if it has ice in it versus if it doesn't have ice. If it doesn't have ice, it immediately starts warming up because it's picking up energy from the room, from your hand, from the table. The ice, though, keeps it from changing temperature. So pure ice, pure water, always 0 degrees C, and it's only once all of the ice is gone that the temperature will start to increase. That's yes. You said it there at the end, yeah. It's not letting the heat from outside get into whatever you're trying to keep cold, or letting the heat out if you're trying to keep something warm. Yep, and it'll stay colder much, much, much longer if you have ice. You can't really do anything to keep it hot longer. But so our heating curve for melting looks very similar to the heating curve for boiling, where we have this flat point, at the melting temperature. And then it's only increasing temperature after all of the ice has melted.
So would it be like lava? Would that be the same thing? The temperature's the same on the lava?
Yeah, if you had rocks are like ice cubes for lava. So the lava wouldn't increase temperature until all of the rocks were melted. That's really weird to think about, yeah. I like that. Rocks are ice cubes for lava. Yeah, so heating curve at melting or at boiling, temperature stays the same. So just like vaporization, we talked about vaporization is endothermic, condensation is exothermic. Melting and freezing are also similarly, where melting is endothermic. It has to absorb heat from the liquid in order to overcome the stickiness to go from a solid to a liquid. And then freezing is exothermic. So whenever you're freezing water, it actually is releasing heat to go from a liquid to a solid. And that one seems counterintuitive because you think of an ice cube when you hold it is cold. Well, the reason it's making your hand cold is because it's melting on your hand, and it's taking heat from your hand to melt. But if you wanted to make it into ice, right, you'd have to be removing heat from the ice cube. This is actually something that farmers around here will use to keep like their citrus from freezing. They'll flood the fields with water, and then if it gets below freezing temperatures, the water has to freeze, and it starts releasing heat to help keep the citrus from freezing. They also move a lot of air. Okay, so just like there was a heat of vaporization, there's a heat of fusion. There's this extra amount of energy that's either released or absorbed, depending on whether you're freezing or melting. So when water is melting, going from a solid to a liquid, delta H is positive. So that means that the water is absorbing energy. The ice is absorbing energy from the surroundings, so it's endothermic. You have to add energy to the ice to melt it, right? You got to heat it up. So then, just like for vaporization, condensation, the opposite process is the opposite in terms of being endothermic or exothermic. So as water freezes, delta H becomes negative because freezing is exothermic. So the process of freezing actually releases heat. And then the calculations for this are the same as for vaporization and condensation. Just need to figure out how many moles of water or whatever substance is freezing or melting, and then use the heat of vaporization or the heat of fusion to calculate that. Which is what this is saying here. Calculate the amount of heat required to melt something. Use the heat of fusion as a conversion factor between the moles of a solid and the amount of heat required to melt them. So again, we're given a mass of ice. So we're going to have 15.5 grams of ice melting at 0 degrees C. So we need to go, yeah, these are for 0. Ice melting 6.02. Let me change this to water, H2O. H2O solid. So what do we need to do first? We want to know how much energy, how much heat is absorbed when this ice cube melts. What did we have to do for the previous problems? Vaporization. Have to find the moles. So we'll use the molar mass of water, because whether it's solid, liquid, or gas, it's still water. So it's still 18.02 grams of H2O for 1 mole of H2O. And this problem gives you a hint as to what the sign should be. I should write this maybe delta H of fusion. So if heat is being absorbed, it says calculate the amount of heat absorbed, what sign does delta H of fusion have? Yes. But is it a positive or negative 6.02? Yeah, positive kilojoules because heat is being absorbed. Remember, this is you're talking about the system as the ice, and is energy going into it or out of it? Is energy being added to the ice? Well, the heat is being absorbed. So like a sponge absorbs water, yeah. So it's going in, so it's a positive. We're adding it. All right, now we can calculate this. 15.5 times 6.02 divided by 18.02. 5.1, let's go 3 sig figs. 5.18 kilojoules of heat.
Giving us that formula too?
I will give you this, the delta H of fusion, and then the delta H of fusion, because it's in units of kilojoules per mole, tells you that you need to find moles, and then multiply by that to get the amount of heat. Could reverse this question and say, like, this amount of heat is given off by a mass of ice melting, or I guess a amount of ice freezing. How many grams of ice froze? And so you would do this in the opposite direction. Take the energy, divide it by the delta H of fusion, and then use molar mass to get the number of grams.
I heard that you can make an ice pack with alcohol and water, because it won't completely freeze if you put it in the freezer.
Mm-hmm.
So what is it, the molecules on each one, they're not sticky?
Yeah, so
Sticky?
the isopropyl alcohol is not as sticky, and so it freezes at a much colder temperature. So there's not enough, the ice can't absorb enough heat when it's melting to get the isopropyl alcohol cold enough that it will actually freeze. So those do make for, especially if you like pulverize the ice. So if you've got really small pieces of ice, you can get like a nice slushy sort of consistency. So for like, yeah, knees or other things, you can like wrap the ice pack around it. So here we have a heating curve for ice beginning at negative 25 degrees C and ending at 125 degrees C. So starting very cold, going up to very hot. So what are the different phases here at A, B, and C? What are the states of water at each of those? So at A is less than 0 degrees C. So water would be, yeah, ice or solid water. What about at B? Well, it's going all the way from 0 up to 100. So that's just water, or maybe I should say liquid H2O. And then C, above 100 degrees C. Steam. Steam, vapor, water, yeah. Gaseous H2O. And in between each of these, there's one of these plateaus, right? So this is melting, where the temperature doesn't change. And this is boiling, where again, the temperature doesn't change until all of that is boiled. So as another hint for what might be on an exam, name the different parts of the graph. So if we needed to calculate the amount of heat in energy or in kilojoules needed to convert 1 mole of ice at negative 25 degrees C, so same graph, all the way up to water at 37 degrees C. So not going all the way to boiling. Yeah, we need all of these values to do that. So this is a simpler combination of concepts here. Because we need Q equals MC delta T for everywhere that we're not at a phase change. So if we're not melting or boiling or freezing or condensing, we need Q equals MC delta T, because we can just take the temperature change up to the phase change and calculate how much heat is absorbed or released. But then once we get to a phase change, the temperature isn't changing. And so Q equals MC delta T. That delta T means T final minus T initial. And during the whole time that we're boiling, or in this case, I guess the whole time that we're melting, the temperature doesn't change, so that would be 0. So Q equals MC delta T doesn't work. And that's where we have to use the delta H of fusion. Let's see. I might have enough room to do this. So on a problem like this, I would recommend drawing out a little graph just so you can see what's happening. So when we start at negative 25, we'll say down here that this is negative 25 at the bottom, and we go up, and then we're going to go up to what temperature? What temperature do things change at? So we do want to get all the way up to 37 degrees C, but if we're starting at negative 25, water melts at 0, or ice melts at 0, right? So when we get to a phase change, then we have to stop and draw a flat line, because the temperature is not going to change once we get to 0 degrees C. And then after we've melted all of the ice, then it can go up again to 35 degrees C. For this one, it's the end of the problem. Oh, I'm sorry. $37, not 35. I think I was thinking 25 and then 35. Okay, so this breaks down our problem into 3 different problems. The first one is the temperature change from negative 25 to 0. So I'm going to label these as A, B, and C.
So then why do we have to do Kelvin on the other one, and in this one we do below 0?
This one because we're only concerned with how much the temperature changes. And because we're only interested in going from one point to another, it doesn't matter if we're in Celsius or Kelvin. And again, you can prove this to yourself. Plug in Kelvin for this, or convert all these temperatures to Kelvin, and you'll get the same answer. So going from negative 25 to 0, we're going to use Q equals MC delta T. And unfortunately, they gave us, so we have 1 mole of ice, but for MC delta T, the M is mass in grams. So this is going to be 18.02 grams of water times, and notice there's a different C for ice. So the specific heat capacity of ice is 2.09 joules per gram degree C. Joules per gram degree C. Times the change in temperature, which is going to be temperature final minus temperature initial. So our final temperature here is 0 degrees C. Our initial temperature is negative 25 degrees C. So our temperature change is positive 25. So 18.02 times 2.09 times 25. Q equals 941.5 joules. Now when we're in section B, now we need the moles of water and the heat of fusion. And so because this is melting, that delta H of fusion is going to be positive, because it's takes energy to melt water or to melt ice. So we can just use 1 mole H2O times 6.02 kilojoules per mole. So that's 6.02 kilojoules. And then for C, we're going to break out Q equals MC delta T again, because now our temperature is changing. And so we can use the temperature change again to calculate how much energy, how much heat it took to heat up the water. So Q, and then the amount of ice, or the amount of H2O hasn't changed. It's still 18.02 grams. One of the things that has changed, though, is our specific heat capacity for water is now 4.184 joules per gram degree C times our temperature change. So T final is going to be 37. And T initial here is not negative 25, but it's the initial part temperature at this section. So we're starting now from 0 degrees C up to the 37. So we've got to break these apart into 3 different calculations. So now 18.02 times 4.184 times 37. And Q is equal to 2,789.6 joules. And then we want to know the total amount of heat in kilojoules. So we convert each of our joules into kilojoules. So times 1 kilojoule over 1,000. And then for sections A, B, and C, we add those all back together. Put units in here, kilojoules plus 6.02 kilojoules plus 2.7896 kilojoules. So 0.9415 plus 6.02 plus 2.7896, and that gives us 9.75 kilojoules of heat. It's a lot. None of the calculations is particularly hard. It's knowing what you need and what to plug in, but yeah, they end up being really long. So